How long could a human really survive in deep space? The answer is more brutal and more surprising than most people think. And once you understand it, space stops looking empty and starts looking deadly. But before we continue, please subscribe to the channel to give your support. Let's continue. Deep space does not kill you all at once. It breaks the human body one system at a time. That is the core of this whole question, and it changes how you should think about survival in space. A lot of people hear, how long could humans survive in deep space? And they treat it like there must be one clean answer, like maybe the limit is food or oxygen or fuel, but that is not how this works. Deep space is not one danger. It is a stack of problems, all pushing on the body and the spacecraft at the same time. And the real limit is usually the first system that starts failing faster than you can control it. So first, we need to be precise. What counts as deep space? Low Earth orbit is not deep space. The ISS is about 400 kilometers above Earth, around 250 miles. And even though that sounds extreme, it is still close to Earth in space terms. More importantly, it is still inside a lot of Earth's magnetic protection. That means astronauts there are not facing the full deep space radiation environment. They are also close enough for relatively fast communication, regular support, and possible emergency return. That does not make the ISS safe, but it does mean it's operating in a much more protected situation than a spacecraft going to Mars. Deep space starts when you leave that protection and start depending almost entirely on your own systems. The moon is about 384,400 kilometers away, about 238,900 miles. Mars is much farther, anywhere from about 54.6 million kilometers to more than 400 million kilometers, roughly 34 million to 250 million miles, depending on where the planets are in their orbits. At that point, the mission is no longer just about travel distance. It becomes a survival problem. Communication delays grow, resupply stops being practical, emergency return becomes hard or impossible, and radiation, isolation, and system reliability become central. So the real question is not just, can humans go far from Earth? The real question is, how long can humans stay alive and functional once Earth is no longer doing most of the protecting? And that brings us to the next part. Survival is not one timer. It is many timers running together. If you lose oxygen, you're in trouble within minutes. If you lose water, the countdown is measured in days. Food gives you more time, maybe weeks or months depending on conditions. But food is only one layer. Radiation damage builds across months and years. Muscle loss starts quickly in microgravity. Bone loss starts early too. Sleep problems grow over time. Psychological stress builds slowly. The immune system can shift. Vision can change. Cardiovascular function changes. So when people ask how long a human can survive in deep space, the honest answer is that survival depends on which failure curve reaches the danger point first. That is what makes this topic so serious. Deep space doesn't usually look like one dramatic event. It looks like multiple small losses happening at once until the mission starts running out of margin. So, what do we already know from real missions? We know that humans can survive for long periods in space. That part is already proven. Many astronauts have spent around 6 months in orbit. Several have gone beyond 300 days. A few have passed 1 full year. Valery Polyakov spent 437 days aboard Mir. Frank Rubio reached about 371 days in space. Those are major achievements, and they matter because they show the human body can stay alive in microgravity for a long time with the right support systems. But there is an important limit to what those missions prove. They were still in orbit around Earth. That means they still had relatively quick communications, regular support, some radiation protection from Earth's magnetic field, and a realistic emergency return path compared with a true deep space mission. A mission to Mars would not have those advantages, so long-duration orbital missions are useful data, but they are not the same as living in deep space. They show endurance, not complete independence from Earth. And that leads to the main point of this section. The biggest limit on deep space survival may not be one dramatic shortage like food or oxygen. It may be the basic fact that the human body evolved for a completely different environment. Your body expects 1G gravity. It expects a thick atmosphere. It expects magnetic shielding from radiation. It expects a regular 24-hour light cycle. It expects constant biological exchange with Earth's environment. It expects normal social contact. All of that is built into human physiology. Remove those conditions for long enough, and the body starts drifting away from normal function. Muscles weaken because they're not being loaded. Bones lose mineral because they're not carrying weight. Sleep can become harder to regulate. Radiation exposure rises across months and years. Stress and isolation change mood and decision-making. The immune system doesn't behave exactly the same way. Vision and fluid balance can shift. None of that means humans instantly fail in space, but it does mean survival is no longer just about staying alive day to day. It becomes a question of how many body systems you can keep stable before one of them becomes the weak point that threatens everything else. And this is why the question matters now more than ever. This used to sound like distant science fiction. It doesn't anymore. Artemis is pushing human exploration back towards the moon. Lunar habitat concepts are being developed seriously. Mars mission plans are being studied in detail. Commercial stations, closed-loop life support, and advanced propulsion ideas are all moving this conversation out of fiction and into mission design. The old view was that the hardest part would be reaching deep space in the first place. Now a more serious idea is taking over. Reaching deep space may be only the beginning. The harder problem may be staying healthy enough to work, think, repair systems, make decisions, and return in one piece after months or years away from Earth. That's the real hook of this entire video. Human survival in deep space is not only about bravery, technology, or distance. It's about whether a body built by Earth can keep working when Earth is no longer there to support it. And once you understand that, the next question gets even more serious. Because before radiation, before food, before psychology, there is an even more immediate problem. How do you stay alive when every breath, every bit of pressure, and every second of survivable air depends on a machine not failing? Vacuum is not the kind of death movies usually show, but that does not make it less deadly. It just makes it faster and less dramatic than people expect. A lot of people grow up with this idea that if a human is exposed to space, the body explodes instantly. That is not true. You do not blow apart, and your blood does not suddenly boil through your skin. But the truth is still bad enough. If you are exposed to vacuum without protection, the danger is immediate. You can lose useful consciousness in roughly 10 to 15 seconds if oxygen is gone, because your brain is suddenly being starved. That is basic hypoxia, not science fiction. And at very low pressure, water and soft tissues can begin to boil, not because it is hot, but because the pressure is too low to keep it in liquid form. That process is called ebulism, and it is exactly the kind of word that sounds technical until you realize it means parts of your body are starting to behave like they no longer belong on a planet. So no, you do not explode, but that correction should not make anyone feel better. The real point is that space does not need spectacle to kill you. It only needs your body to be outside the pressure range it was built for a very short amount of time. And that leads to the next problem, because vacuum is only the extreme version of a more important rule. In deep space, air is not natural. It is manufactured every second. On Earth, you never think of air as a machine output. You breathe, and the atmosphere is simply there. Pressure is there. Oxygen is there. Carbon dioxide is diluted away. Humidity, temperature, and trace gases stay within a survivable range because the entire planet is doing environmental control for you all the time. In a spacecraft, none of that exists unless the hardware keeps producing it. A habitable cabin means pressure has to stay stable. Oxygen partial pressure has to stay in a narrow range. Carbon dioxide has to be removed continuously. Humidity has to be managed. Temperature has to be controlled. Toxic trace chemicals have to be filtered out. Airflow has to move properly so you do not get stagnant pockets of bad air around the crew. That means every breath in deep space is the result of pumps, valves, scrubbers, seals, sensors, software, and power systems all continuing to work together without serious drift. This is why a spacecraft is not just a vehicle, it is a life support factory. It has to fake part of Earth every second, and it has to do it so well that the crew can almost forget how artificial everything is. The second they do remember, it is usually because something has started to go wrong. And one of the first things that can go wrong is not lack of oxygen, but too much carbon dioxide. That sounds backwards at first, because most people assume oxygen is the main problem. Oxygen matters, obviously, but carbon dioxide can become dangerous much earlier in a more subtle way. On Earth, carbon dioxide in the atmosphere is only about 0.04%, around 420 parts per million today. That is extremely low compared with what can happen inside a spacecraft. Spacecraft environments can run much higher, and the important point is that levels do not need to be high enough to kill you in order to start harming the mission. That is what makes carbon dioxide such a serious threat. It can damage performance before it causes collapse. Even modest buildup can lead to headaches, poor sleep, slower thinking, trouble focusing, irritability, and worse decision-making. In deep space, that is not a comfort issue. That is an operational issue. A crew does not need to be unconscious for air quality to become dangerous. They only need to become a little slower, a little less sharp, a little more tired, and a little worse at solving problems. In a mission where every repair, every checklist, and every decision matters, slightly bad air can become a full mission-level threat. That is one of the most important things to understand about deep space survival. Catastrophic failure is not the only danger. Chronic underperformance can be just as serious. A crew with mildly elevated carbon dioxide may still be alive, still talking, still doing tasks, but doing them worse. And in deep space, worse is sometimes enough. So if the air itself has to stay within tight limits every hour of every day, what happens when the pressure vessel starts to fail? This is where a lot of people think of the Hollywood version again. One big hole, one explosive decompression, everything over instantly. Real life is usually less theatrical and more dangerous in a different way. A tiny micrometeoroid puncture, a degrading seal, a valve that no longer closes properly, a hidden crack caused by repeated thermal cycling. These are not always instant death, but in deep space, they do something almost worse. They start a countdown. A spacecraft can lose pressure slow enough that the crew has time to respond, but that doesn't mean the problem is manageable forever. In low Earth orbit, there are more options. There may be nearby modules, more help from the ground, more spare parts, more chances for resupply, more realistic emergency plans. On a Mars transfer vehicle, those options shrink hard. There is no repair crew coming. There is no quick docking fallback. There is no fast abort to Earth. The same leak that is a serious maintenance problem near Earth can become a long-term survival crisis in deep space. And even if the leak is found, fixing it is its own challenge. The crew has limited tools, limited parts, limited time, and limited error to make. Every repair uses supplies. Every emergency procedure increases stress. Every patch has to hold not just for an hour, but maybe for months. That's the real difference distance creates. In deep space, damage does not just threaten the vehicle, it reduces the size of the safe world the crew lives inside. That's really what pressure vessel is. It's not just a technical number. It's the boundary between a human environment and a fatal one. Inside that pressure vessel, the body can still work. Outside it, the rules change immediately. And once you see that, the deeper point becomes hard to ignore. Deep space survival is not about toughness in the way people usually mean it. It's not about being fearless or enduring pain or being mentally strong in some vague heroic sense. None of that can help you if the pressure falls too far, the air chemistry drifts too far, or the life support system stops doing its job. The body does not negotiate with physics. It does not care how motivated you are. It does not reward courage with oxygen. It does not reward pressure with discipline. Either the machine keeps creating a small Earth around you continuously and precisely, or your body starts failing on a very short timeline. That is the first brutal lesson deep space teaches. Survival is not you versus the void in some romantic sense. Survival is you staying inside a machine that can imitate Earth well enough, second by second, year after year, without drifting too far outside the limits your biology can tolerate. And once that becomes clear, the next question gets worse. Because even if your spacecraft keeps the air breathable and the pressure stable, there's another limit you hit very quickly. How long can humans survive when the most ordinary thing on Earth, water, becomes one of the hardest, heaviest, and most unforgiving parts of the entire mission? Water looks simple on Earth, but in deep space, it becomes one of the main things that decides whether the mission works at all. People usually think of water as just one more supply item, like food or medicine. But water is much more than that. It's one of the first hard limits of survival, and it shapes the whole spacecraft around it. You can survive only a few days without it in harsh conditions, and deep space is nothing if not harsh. But even that basic survival fact is only the beginning. In a mission, water is not just for drinking. You need it to prepare food. You need it for hygiene. You need it for cleaning. You may need it for cooling systems. In some designs, you also use it to help produce oxygen through electrolysis. So when people ask how long humans could survive in deep space, one of the first honest answers is this: you run out of water before you run out of plans. And the numbers get serious very quickly. A person may need roughly 2 to 4 liters of water per day, about half a gallon to 1 gallon, just for drinking and basic metabolism. That is a minimum layer. The total water demand of the mission is much higher, unless you can recover and reuse most of it. Once you include food systems, humidity control, sanitation, and other onboard needs, water stops being a personal supply and becomes part of the habitat's operating system. So the next question is obvious. Can't you just recycle it? Yes, and that is already one of the major achievements of human spaceflight. Modern spacecraft systems, especially on the ISS, already reclaim water from humidity in the air, from urine, and from other waste streams. Recovery rates in some systems have gone above 90%. That is an impressive level of engineering. On Earth, that kind of recycling would sound extreme. In space, it is normal because it has to be. But here's the problem. Above 90% sounds nearly perfect until you stretch it across a very long mission. A system that loses only a small percentage each cycle can still create a major supply problem over time. On a Mars-class mission lasting roughly 900 to 1100 days, including travel and surface stay, even a small loss fraction adds up to a large mass penalty. If you cannot recover that missing water, you have to launch more of it from the start. And water is heavy. Every extra liter has to be accelerated off Earth, moved through space, protected, stored, monitored, and kept clean. That is where the water problem stops being about biology and becomes architecture. It changes the mass budget. It changes the vehicle design. It changes how much margin the mission has. It changes how much cargo space is left for everything else. And then the story gets more serious because water is not just a consumable, it can also protect you. Water is useful as radiation shielding, especially against some kinds of charged particles because hydrogen-rich materials can help slow them down. That gives water a second job. It is not only something the crew drinks, it is also something mission designers may want to place around crew areas to reduce radiation exposure. In other words, every kilogram of water can do double duty. It supports life directly, and it can help protect life indirectly. That matters because mass in deep space has to justify itself. Water does. 1 liter of water has a mass of about 1 kilogram, and in imperial terms, that is about 2.2 pounds. That may not sound like much until you scale it up. Hundreds or thousands of liters become hundreds or thousands of kilograms, or many thousands of pounds. Launching that mass is expensive. Carrying it is difficult, but not carrying enough of it creates a survival problem. That is why water becomes one of the most valuable substances on the entire mission. It is heavy, costly, and still almost impossible to replace once you leave Earth. So if recycling is essential and water also has shielding value, then the next question is even tougher. How reliable does the recovery system have to be? The answer is extremely reliable because a closed-loop water system is not one machine. It is an entire chain of machines and control steps. You have filters, you have pumps, you have membranes, you have reservoirs, you have monitoring sensors, you have chemical treatment, you have microbial control, you have maintenance procedures, you have software checking whether the chemistry is drifting. Each part may work well on its own, but the crew survives only if the whole chain stays stable together. That is where failure becomes complicated. Filters can clog, pumps can wear down, membranes can degrade, sensors can drift, biofilms can grow, microbial contamination can spread in places you do not want it. A reservoir can stay technically full and still become unsafe if the chemistry is wrong or the biology inside it changes. And unlike a simple supply tank, a recycling system has moving parts, monitoring needs, and maintenance demands. That means every day the system saves mass, it also creates dependence. In low Earth orbit, dependence is serious but manageable because replacement parts and troubleshooting support are more realistic. In deep space, those same weaknesses become much more dangerous. A failed component may not be replaceable. A microbial problem may not be easy to isolate. A slow decline in water quality may force the crew to spend more and more time on repairs, testing, and workarounds. At that point, the water system is still technically functioning, but the mission is being pulled toward maintenance. And that changes the role of the crew. The farther humans go, the more they stop being passengers and even explorers in the usual sense. They become caretakers of a small artificial world that has to keep cycling its own water, air, and waste without drifting into failure. The question is no longer just, do we have enough water? The real question becomes, can this habitat stay chemically and microbially stable for years without turning the crew into full-time mechanics? That is a much harder question because deep space does not reward systems that work most of the time. It rewards systems that stay stable for a very long time under constant use, limited repair options, and no outside rescue. And that brings us to the deeper conclusion of this whole section. The survival limit in deep space is partly a water mathematics problem, but not in the simple way people mean. Of course, humans need water. Everybody knows that. What matters more is that water forces the shape of the mission itself. Its mass affects launch design. Its recycling efficiency affects mission duration. Its contamination risk affects crew health. Its storage affects internal layout. Its recovery hardware affects maintenance demands. In other words, water is not just something on the spacecraft. It helps determine what kind of spacecraft you can build in the first place. That is why this topic is bigger than thirst. On Earth, needing water is ordinary. In deep space, the same need becomes one of the main reasons the entire mission has to be carefully engineered from the inside out. And once you see that, the next problem becomes unavoidable. Because even if you solve water storage, water recycling, and water safety, there's still another question that gets harder the longer the mission lasts. Can you feed the human body for years in space, not just with enough calories to stay alive, but with enough stable nutrition to stop it from slowly breaking down? Food is one of those things that sounds solved until you ask a more serious question. Not can you bring enough to eat, but can that food keep a human body healthy for years? For a short mission, food is mostly a storage problem. You calculate calories, pack the mass, manage the menu, and move on. But deep space turns food into something more difficult. It becomes a stability problem. On paper, it is easy enough to estimate how much energy a crew needs. Nutrition plans can be built, meal schedules can be organized. The trouble starts when you stretch the mission from months to years. Stored food does not stay biologically perfect forever. Vitamins degrade, texture changes, packaging slowly ages, flavor gets worse. Some nutrients, especially vitamins like C and K, can drop over time in stored foods. So the real question is not, do you have enough meals loaded onto the ship? The real question is, After 2 or 3 years, are those meals still doing the job a human body needs them to do? That difference matters more than it sounds. A person can be eating enough calories and still be drifting into nutritional trouble. That is the danger. In deep space, food is not just fuel, it is long-term support for muscles, bones, blood, immunity, healing, mood, and cognition. If the nutritional quality slowly drops, the damage may not look dramatic at first, but over a long mission, small deficiencies stop being small. And that leads to the next problem, because even before food quality becomes an issue, space already makes it harder for people to eat enough. Astronauts commonly lose body mass during missions. That is already part of the record from orbit. Energy intake can fall below what the body actually needs. There are several reasons for that. Taste can change, congestion from fluid shifts can make food seem less appealing, motion sickness can reduce appetite, especially early in missions, workload matters, stress matters, routine matters. Sometimes the crew is simply too busy or too uncomfortable to eat as much as they should. On Earth, skipping meals is usually just a bad habit. In deep space, chronic undereating becomes part of a much bigger decline. If calorie intake stays too low for too long, muscle loss speeds up, fatigue gets worse, recovery gets worse, immune strength can weaken, mood can drop. And the dangerous part is that this can happen gradually. Nobody has to collapse for the mission to be getting worse. The crew can still function, still do tasks, still look mostly okay from the outside, while slowly losing physical margin. And the farther the mission goes, the less room there is for that kind of slow deterioration. In low Earth orbit, you may be able to absorb some nutritional imperfection and recover later. In deep space, later may be too far away to help. So if stored food becomes less ideal over time and appetite is already unreliable, then the obvious next idea is fresh food. Why not grow some? That sounds like a clean solution, and in some ways it is. Fresh plants could provide micronutrients that stored food loses over time. They could support morale. They could make the habitat feel less artificial. In some systems, plants may even help with oxygen support and humidity cycling. There have already been orbital experiments growing lettuce, zinnias, peppers, and other crops. So this is not fantasy. It is real research and it points towards something important. But growing food in space is much harder than it sounds. Agriculture on Earth gets huge amounts of help for free from gravity, climate, soil ecosystems, open air, sunlight, and scale. Space agriculture gets none of that for free. If you want plants in a spacecraft, you need lighting, you need water control, you need nutrient delivery, you need contamination management, you need volume, you need crew time, you need hardware that works reliably. And every one of those things has a cost in mass, power, maintenance, and complexity. That is why growing even a small amount of fresh food is not a trivial upgrade. Every leaf has to justify itself. Every tray of plants has to earn the space it takes up. In a deep space vehicle, volume is limited, power is limited, water is limited, and crew labor is limited. So even if fresh food gives biological and psychological benefits, it also creates a new system that has to be managed, repaired, monitored, and protected from failure. A salad sounds simple on Earth. In space, it becomes part of the life support argument. And the deeper you go into that logic, the more you realize food is not separate from the rest of the mission at all. It interacts with almost everything else. Nutrition affects fluid balance, sodium intake matters there, protein intake matters for muscle preservation. Vitamin D and calcium connect to bone health, even though bone loss and microgravity is not something you can solve with supplements alone. The body loses bone because it's being unloaded, and no menu can fully cancel that. Antioxidants may help with some cellular stress responses, but they don't erase radiation exposure. The point is that food becomes part of the medical strategy, but only part of it. It can support the body, it can reduce some risks, it can help preserve function, but it cannot fully replace gravity, and it cannot neutralize galactic cosmic rays. That's an important correction, because people often want one solution. They want to believe there's a perfect diet for space, something that keeps muscles, bones, immunity, and cognition all stable at once. The evidence does not support that kind of simple answer. Nutrition matters enormously, but it works inside a larger system of stress, radiation, sleep, exercise, fluid shifts, and isolation. So yes, the menu becomes medicine, but only partial medicine. And that's where this section shifts from logistics to something much bigger. A short mission can absolutely survive on packaged food. That part is within reach. But a truly long mission may need a different model entirely. It may need to move away from food as cargo and toward food as production. That's a major change. It means the spacecraft starts behaving less like a vehicle carrying supplies and more like a controlled ecosystem trying to regenerate some of its own biological support. That's a hard transition, because cargo is simple compared to ecology. Stored food doesn't grow mold because it feels like it. Plants do. Stored food sits there until you eat it. Agriculture is active, living, unstable, and sensitive. But once missions get long enough, production starts looking less optional because storage alone may no longer guarantee health. And this is the real high-stakes pivot in the whole food discussion. Once you need the spacecraft to do more than carry meals, once you need it to preserve nutrition actively, or even produce part of it, the mission changes category. You're no longer asking only how long humans can live in space with enough supplies. You're asking how much of Earth's biological support system can be rebuilt inside a machine. That's the harder question, and it keeps showing up in different forms. Water becomes architecture, air becomes engineering, food becomes ecology. And once that happens, the next problem gets even more direct, because even with enough water and enough food, your body still starts changing almost immediately in a way no meal plan can stop. What happens when gravity disappears and your body starts treating muscle and bone like unnecessary weight? Microgravity does not just make you float. It starts changing your body almost right away. And a lot of those changes move in exactly the wrong direction for long-term survival. That is one of the biggest misconceptions people have about space. Weightlessness looks clean, smooth, even comfortable. People see astronauts drifting and think it must be easier on the body because everything feels light. But your body does not read microgravity as freedom. It reads it as a completely different operating condition. And once that happens, it starts cutting back on systems it no longer thinks it needs. On Earth, gravity is loading your body all the time. Every second you stand, walk, climb, lift, or even just sit upright, your muscles and skeleton are dealing with a constant pull. Your postural muscles are always working. Your bones are always being stressed enough to justify staying strong. That stress is not damage, it is instruction. It tells the body, keep the structure, we still need it. Take gravity away and the instruction changes. In microgravity, the body quickly starts treating some of its own support systems like extra cost. Muscle atrophy begins fast, especially in muscles that normally help you stand and move against gravity. Things like the legs, hips, back, and core. Bone loss is just as serious. In some weight-bearing areas, bone mineral can drop by roughly 1 to 1.5% per month without strong countermeasures. That is an extreme rate compared with normal age-related bone loss on Earth. On a long mission, that is not a side effect. That is a major structural problem. And what makes this worse is that the body is not malfunctioning in some random way. It's adapting exactly as biology often does. It's saving resources. If a tissue is no longer being used the way it was on Earth, the body starts reducing its investment in that tissue. That is efficient in one sense, but dangerous in another, because you're still going to need strength and bone integrity later. The body is adapting to survive in microgravity, not to perform well when gravity comes back. So the next question is obvious. Can exercise stop that? Exercise helps a lot, but it does not solve the problem completely. On the ISS, astronauts use treadmills, stationary cycling systems, and resistive exercise devices for around 2 hours a day when you include setup and transitions. That is not normal fitness, and it's definitely not optional. It's more accurate to think of it as anti-degeneration medicine. They are not training to get stronger than normal, they're training to slow down the losses that space is already trying to impose on them. That's an important distinction. On Earth, exercise usually improves you. In space, exercise is often trying to stop you from getting worse. And even with good exercise systems and disciplined routines, losses can still happen. Muscle size can still fall, strength can still decline, bone density can still drop. So the current reality is not that exercise fixes microgravity. The reality is that exercise buys you time and reduces the damage. That is valuable, but it is not the same as a full solution. This is where the problem becomes more serious than a simple health issue. Exercise takes time, it takes energy, it takes equipment, it takes maintenance. The machines have to work. The crew has to stick to the protocol. So now the mission has another permanent demand built into it. The astronauts are not just explorers or operators. They're people who must follow a strict daily physical preservation program simply to avoid arriving weaker than the mission can tolerate. And that leads directly to the hardest part of the whole issue, because surviving in weightlessness is only half the story. The real test begins when gravity comes back. This is one of the most uncomfortable truths in long-duration spaceflight. You can stay alive in microgravity while becoming less capable of functioning in gravity. That matters immediately for any mission beyond orbit. Mars has a gravity of about 0.38 g. The Moon has about 0.165 g. Those are not Earth levels, but they are still enough to make physical weakness matter. After months in microgravity, standing up, walking, lifting equipment, reacting quickly, and maintaining balance can all become harder. Your muscles are weaker. Your cardiovascular system has adapted to a different environment. Your body has spent months behaving as if gravity was no longer important, and now suddenly it is important again. So when people ask whether humans can survive a trip to Mars, the answer cannot just mean alive on arrival. That is too low a standard. The real question is whether the crew arrives able to function. Can they get out of the vehicle safely? Can they move in pressure suits? Can they handle emergencies? Can they repair equipment? Can they do all of that after a long transit when their bodies may already be deconditioned? That is why return to gravity matters so much. It exposes the difference between surviving a space journey and completing one successfully. A crew that lands alive but physically degraded is not in a good position, especially if the mission depends on immediate work. And then the next question gets even more unsettling, because maybe Mars gravity itself helps. Maybe it's enough to slow the damage once the crew gets there. But how much does it help? Right now, that is still one of the biggest unknowns in human space exploration. We know a lot about what happens at 0 g because we have orbital data. We know a lot about life at 1 g because that's normal Earth biology. What we don't know nearly well enough is what happens over long periods at partial gravity, especially levels like the Moon's or Mars's. Is 0.38 g enough to preserve bone better than 0? Probably at least somewhat. Is it enough to preserve muscle, circulation, balance, and long-term health in a reliable way? That is much less clear. Maybe it helps enough to keep humans functional. Maybe it helps only partly, and the slow decline continues. If it is only partial, then Mars is not just a difficult destination. It may become a place where biology keeps drifting in the wrong direction over time, only more slowly than during transit. That is why this is not just a scientific curiosity. It's an operational question with huge consequences. If Mars gravity is enough, the mission architecture looks one way. If it is not enough, then deep space missions may need much more aggressive countermeasures. Maybe artificial gravity, maybe stronger exercise systems, maybe different habitat designs. The answer changes the whole strategy. And this is where a lot of old assumptions break apart. There was a long-standing fantasy in the space age that humans are basically generalist adaptables. In one sense, that's true. humans do adapt, but the data shows something more troubling. The body often adapts in ways that help short-term survival in that environment while reducing performance for the environment you eventually need again. That's the key difference. Adaptation is not always the same as preservation. Your body adapts away from Earth. It adapts to not needing full skeletal support, not needing the same cardiovascular response, not needing the same muscle loading. And then, the moment you need Earth-like performance again, or even Mars-like performance, you discover that the body's adaptation has a cost. It has become better suited for floating and less suited for standing, lifting, moving, and enduring gravity. That changes the entire emotional logic of deep space travel. The risk is not only that space kills you, the risk is that space keeps you alive while steadily making you less capable of doing the things needed to survive the next stage of the mission. That is a different kind of danger, and in some ways a worse one, because it can look manageable until the exact moment performance matters most. And once you understand that, the next threat becomes even harder to ignore, because muscle and bone loss are at least things you can feel and measure. The next danger is more silent than that. What happens when the thing most likely to define the upper limit of human survival in deep space is something you cannot feel at all? Radiation moving through your body, particle by particle, month after month. Radiation is probably the most important threat in deep space, and the worst part is, you cannot feel it while it is happening. That is what makes it different from almost every other danger in space. If air pressure drops, you notice. If water runs low, you notice. If your muscles get weaker, you notice. Radiation is different. It can be passing through your body, through the walls of the spacecraft, through your organs, through your DNA, and you may feel absolutely nothing in that moment. But the damage can still be building the entire time. And the first thing to understand is that space radiation is not one single threat. It is several different threats layered together. There are trapped radiation belts around Earth, often called the Van Allen belts. There are solar particle events which can send intense bursts of energetic particles out from the sun, especially during solar storms. And then there are galactic cosmic rays, which are high-energy particles coming from outside the solar system. These are not all the same. They come from different sources, they behave differently, and they create different kinds of risk. In low Earth orbit, astronauts still get more radiation than people on Earth, but they also still benefit from a big advantage. Earth's magnetic field blocks a significant part of the incoming radiation environment. That does not remove the danger, but it cuts it down. Once you go into deep space, that shield falls away. The crew is more exposed, for longer, with fewer places to hide. And that changes the mission completely. A solar storm can hit with a high dose over a short period. Galactic cosmic rays are different. They are not one dramatic burst. They are lower rate but constant, and they are extremely energetic. They can penetrate shielding and damage tissue at the cellular level. That is why radiation in deep space is not just an engineering issue, it's a biological issue, and it's happening all the time. So the next question is, how serious are the numbers really? Serious enough that we already have data pointing to a real limit. Astronauts in orbit receive more radiation than people on Earth, and that is well established. But for deep space missions, especially Mars missions, the expected exposure becomes much more concerning. Data collected during the Mars Science Laboratory cruise helped scientists estimate that a round-trip human-Mars mission could involve radiation doses on the order of several hundred millisieverts, potentially around or above 0.6 to 1 sievert depending on shielding, route, timing, and solar conditions. That is a completely different scale from normal life on Earth. Earth's average background radiation exposure is only a few millisieverts per year, so when you start talking about deep space missions, you are no longer dealing with a small increase over normal life. You are dealing with a level of exposure that becomes a central mission parameter. And that matters because radiation risk is not just about whether a dose is instantly lethal. That's too narrow. A crew can survive the mission and still accumulate damage that raises their long-term risk significantly. In deep space, surviving the trip is only one part of the radiation story. The body may still be carrying the cost later. And that takes us to one of the most important distinctions in this whole topic. Acute radiation and chronic radiation are different problems. A major solar particle event is the acute version. If the crew is exposed without good storm shelter protection, the dose can become high enough over a short period to threaten acute radiation sickness. That is the immediate nightmare. A crew may need to move into a better shielded part of the spacecraft and stay there until the event passes. That is one reason storm shelters are such a serious design requirement in deep space mission planning. But galactic cosmic rays are worse in a different way. They don't usually arrive as one big emergency that everyone notices. They are a long, quiet exposure problem. Over time, they may increase the risk of cancer, cataracts, cardiovascular injury, degenerative tissue effects, and possibly central nervous system damage. That is why they are so hard to deal with. There may be no dramatic moment when the mission suddenly becomes unsafe. The damage just keeps accumulating. And that creates a very different kind of psychological problem too. Humans are better at responding to visible threats: fire, impact, decompression. Those are easy to understand because they are immediate. Radiation doesn't work like that. It's invisible, delayed, and cumulative. You won't feel a cosmic ray passing through your body. You won't hear a warning from your nerves. But that doesn't make it minor. It makes it harder to fight. So then the obvious solution sounds simple. Just add more shielding. But shielding is where this problem becomes much more complicated. A lot of people assume the answer must be something dense like lead. That sounds intuitive. If you want to block dangerous radiation, use heavy metal. But deep space radiation is not that simple. With high-energy cosmic rays, heavy atomic number materials can actually create secondary particle cascades when struck, meaning the shielding can produce more complicated radiation effects instead of just blocking them cleanly. So the best answer is not always the densest material. That's why hydrogen-rich materials like polyethylene or water are often considered more useful in some situations. They can be better at slowing certain charged particles without creating the same kind of secondary effects. That sounds promising, and it is, but it doesn't solve the mass problem. Every shielding strategy costs weight. Every extra protective layer adds mass to the spacecraft. And in spaceflight, mass is one of the most expensive things you can ask for. More mass means more launch demand, more propulsion demand, more structural demand, and less room for everything else. So shielding is never just a safety decision. It's also a mission design trade-off. That's the brutal part. The safer you want the spacecraft to be, the heavier it gets. The heavier it gets, the harder and more expensive it is to move. And the farther you are going, the more painful that trade-off becomes. So there is no perfect answer waiting here. Mission designers are trying to reduce exposure, not eliminate it completely, because complete elimination is not currently realistic. And that leads to the real conclusion of this section. Radiation may set the upper limit of human deep space survival more than almost anything else. You can improve life support. You can recycle water more efficiently. You can carry more food. You can exercise to slow muscle and bone loss. You can train harder, plan better, and design smarter systems. But radiation doesn't care about discipline, and it doesn't stop because the crew is prepared. It's built into the environment itself. That is what makes it so important. It's not just another hazard on the checklist. It may be the background condition that decides how long humans can really stay out there before the biological cost becomes too high. And the longer the mission lasts, the worse that trade-off gets. Days are one thing, months are another. Years is where the problem starts becoming much more serious, because every extra week in deep space means more particles, more exposure, more cumulative damage, and more uncertainty about what that damage means by the end of the mission and long after it. So, when people ask how long humans could survive in deep space, radiation is one of the clearest reasons the answer is not unlimited, not even close. It is one of the main forces pushing back against every long duration plan. The universe is not just empty space around you, it is an active environment, and over time, it reaches into the body itself. And once you understand that, the next problem becomes even more unsettling, because radiation is not the only invisible thing changing in deep space. What happens when the spacecraft is still intact, the crew is still alive, but the mind inside that spacecraft starts getting slower, more stressed, less precise, and a little less like itself? A deep space mission can fail even if nothing breaks on the spacecraft because the people inside it can start breaking first. That is the part of space survival people often underestimate. We talk about propulsion, radiation, life support, shielding, and pressure systems, and all of that matters. But a long mission is also a test of attention, mood, judgment, memory, discipline, patience, and social stability. And those are not soft issues. In deep space, they are operational issues. A crew does not need to panic or completely fall apart to be in danger. They only need to become a little more tired, a little more irritated, a little less careful, and a little less able to think clearly under pressure. That is why isolation has to be taken seriously as biology, not just emotion. A deep space mission separates you from Earth physically, obviously, but also socially and neurologically. You are confined to a small environment, the same walls, the same people, the same routines, the same equipment, the same work cycles day after day. There is monotony, there is pressure to perform, there is constant awareness that mistakes matter. Sleep may already be disrupted, workload may already be high, and under all of that, the brain's still trying to regulate stress, attention, and mood in a setting that human beings did not evolve for. We already have clues from analog missions on Earth. Antarctica, underwater habitats, and sealed habitat studies repeatedly show similar patterns. Sleep disruption shows up again and again. Tension cycles build over time. People become less tolerant of novelty. Small annoyances can become bigger than they should be. In some cases, performance declines. That does not mean these environments always produce failure, but it does show that isolation and confinement change how people think and behave. And in deep space, the stakes are higher because there's no real escape from the environment. You cannot go outside for fresh air. You cannot walk away from the team. You cannot reset your minds with normal life. The habitat is the whole world, and that means psychological pressure has nowhere to go except into the people living there. Then the next problem makes that even harder because in deep space, even communication with Earth stops feeling normal. A signal between Earth and Mars can take roughly 4 to 24 minutes one way, depending on where the planets are. That means there's no such thing as real-time conversation in the middle of a crisis. No live coaching, no instant troubleshooting, no immediate emotional support. A crew can be dealing with an injury, a technical failure, or a serious conflict, and mission control is still responding to conditions that already changed many minutes ago. That delay does more than slow down operations. It changes the whole command structure. In low Earth orbit, crews can work in close coordination with the ground. In deep space, they have to operate much more autonomously. They have to make decisions without waiting for reassurance. They have to solve technical problems without assuming instant expert input. They have to manage stress without immediate outside support. That means deep space crews do not just need technical independence, they need psychological independence too. They need to function under the feeling that when something serious happens, help is not absent but late, and late matters. Even if mission control gives the correct advice, the crew still has to survive the delay, make decisions in the gap, and carry the emotional weight of knowing that in a real emergency, Earth is effectively talking from the past. And then there's another layer that makes this even more unsettling. The environment may not only affect how the crew feels, it may affect the brain physically. MRI studies of astronauts after long-duration missions have shown changes linked to fluid shifts and altered brain position. Researchers have observed things like ventricular enlargement and changes in cerebral spinal fluid distribution. That does not mean astronauts are becoming non-functional or that the brain is being destroyed in some dramatic sense, but it does mean the central nervous system is involved in the adaptation to space, and that adaptation is not small enough to ignore. This matters because deep space missions are built on cognition. The crew has to manage systems, interpret data, follow procedures, improvise repairs, and make careful decisions under stress. stress. So if the brain and the fluid environment around it are changing over time, that becomes a mission concern, not just a medical curiosity. The point is not that astronauts suddenly lose the ability to think. The point is that long missions may be changing the nervous system in ways we still don't fully understand. And uncertainty is already a risk factor when the mission is this demanding. So now put all of that together: stress, confinement, delayed communication, sleep disruption, and possible nervous system changes, and you get to the next issue. The crew is not just a collection of individuals, it's a small emotional system. This is where team conflict becomes a real mission variable. A Mars crew is not just several highly trained people doing jobs side by side. It's a closed social environment that has to stay functional for months or years. Small resentment can become chronic friction. One person's bad habit can become another person's daily source of stress. A communication style that feels manageable in month 1 may become exhausting in month 9. None of this needs to become dramatic to be dangerous. That's the key point. Deep space conflict does not need to turn into open hostility or some movie-style breakdown. It only needs to make the crew slightly worse at working together. A little less trust, a little more hesitation, a little more tension in checklists, repairs, decisions, and handoffs. That's enough. Because in deep space, procedural sloppiness is not just annoying, it's how small failures become bigger failures. Even elite crews are still human. Careful selection helps, training helps, conflict management helps, but no selection process turns people into machines. Stress changes behavior, fatigue changes tone, repetition changes patience, and judgment, if it erodes by even a small amount, that can matter a lot in an environment where nearly everything depends on consistent performance. That is why the mental world of the crew may be just as important as the engineering world around them. We often frame deep space as a hardware challenge. Build the right ship, build the right shielding, build the right systems, and the mission works. But that's only part of the truth. The spacecraft can still be technically intact while the people inside it become more tired, less motivated, less precise, and less resilient. Radiation may damage cells, isolation may damage coherence, delayed communication may damage confidence, chronic stress may damage discipline. None of those things need to fail all at once for the mission to become more fragile. And this is the deeper twist in the whole discussion. Survival is not just whether the ship still flies. Survival is whether the minds inside that ship are still functioning well enough together to keep everything else running. The crew has to remain a team, not just a set of individuals who are still technically alive. In deep space, that distinction matters a lot, because if the ship is holding pressure, if the life support is running, if the food and water are still available, but the crew's attention, trust, energy, and precision are all drifting downward, then the mission is still moving toward danger, just more quietly. And once you understand that, the next section gets even stranger, because the brain is not the only part of the body being affected by weightlessness in ways that are easy to underestimate. What happens when living without gravity starts changing your eyes, your blood flow, and the fluid physics inside your own body? Some of the most serious changes in space do not come from impact, fire, or decompression. They come from fluids moving to the wrong place for too long. That sounds minor at first, because fluid shift does not sound like a dramatic problem. But in microgravity, gravity stops pulling blood and other body fluids downward the way it does on Earth. So those fluids redistribute upward toward the chest and head. Astronauts often notice this quickly. Faces can look puffier, legs can look thinner. At first, that almost sounds cosmetic, like an odd side effect of floating. It is not. It is a sign that the internal fluid balance of the body has changed. And once that shift happens, the consequences start spreading through multiple systems. Pressure relationships around the brain can change. Venous drainage changes. The circulation around the eyes changes. The body is now operating under a fluid pattern it was never really designed for over long periods. That is one of the repeating themes of deep space. The danger often begins with something subtle. A puffy face does not sound like a mission threat until you follow the chain far enough and realize it may connect to vision, pressure regulation, and long-term performance. That brings us directly to one of the clearest warnings in this whole area. Changes to the eyes are real, documented, and serious enough to have their own name. Some astronauts on long-duration missions have developed changes in vision and changes in eye structure. These include optic disc edema, flattening of the back of the eyeball, and refractive shifts, meaning vision can change in ways that matter operationally. This collection of findings is now called Spaceflight-Associated Neuro-Ocular Syndrome, or SANS. Not every astronaut gets the same severity, and not every case produces major functional problems, but that does not make it a minor issue. The fact that long-duration spaceflight can produce persistent ocular changes at all is a major warning sign, because in a deep space mission, vision is not just convenience, it is a working system. The crew may need sharp vision for landing, repairs, instrument reading, emergency response, navigation tasks, medical procedures, and EVAs. If visual changes build over time, that is not just a medical side effect sitting quietly in the background. That is a direct systems threat. A mission depends on the crew seeing clearly and working precisely. If the visual system starts shifting in the wrong direction, that affects the mission's margin for error. And the unsettling part is that SANS is still not fully understood in a complete operational sense. Researchers have strong clues about fluid shifts, pressure changes, and altered drainage, but there is still active work being done to understand exactly why some people are affected more than others, and what the best long-duration countermeasures should be. That uncertainty matters. A known problem with an incomplete solution is exactly the kind of thing that becomes more dangerous the farther you go from Earth. And the eyes are only one part of the story, because the same weightless fluid environment is also changing the blood and the cardiovascular system. In space, plasma volume can decrease, cardiovascular reflexes can change. The circulatory system starts adapting to a place where standing up against gravity is no longer part of daily life. On Earth, gravity is constantly forcing your circulation to do work. Your blood vessels, your heart, and your autonomic nervous system are continuously managing pressure changes. When you stand up, the body has to respond immediately to keep blood flowing properly to the brain. That training never stops on Earth. In space, that demand drops away, and the body responds to that too. This is why astronauts can experience orthostatic intolerance when they return to gravity. That means the body can struggle with standing upright without dizziness or weakness, because the circulation is no longer as ready for that challenge. In a sense, the body has been trained into the wrong environment again. It has spent months acting as if gravity is no longer a major requirement, and then suddenly Mars or Earth asks for performance that the cardiovascular system is less prepared to deliver. That matters a lot for deep space missions, because once again, survival is not just arriving alive, it is arriving able to function. If a crew reaches Mars after a long transit and their circulation is less able to support standing, movement, and rapid physical response, then every surface operation gets harder. The body has adapted to the transit in a way that may reduce readiness for the destination. And then there's another layer that makes this even more concerning, because the cardiovascular changes in space may include risks we did not fully expect earlier in the history of human spaceflight. One of the more unsettling findings in recent years is that changes in venous blood flow in microgravity may create unexpected vascular risk patterns, including concerns involving thrombosis. In other words, clot-related problems. This is the kind of discovery that changes the emotional tone of the whole subject. It is one thing to deal with expected problems like muscle loss and bone loss. It is another thing to discover that the body may also be vulnerable to failure modes we were not even prioritizing before. That is what makes this area so uncomfortable. Space medicine is still learning in real time which systems are most fragile in a long-duration environment. A clot risk, a drainage problem, an eye pressure issue. These are not dramatic in the Hollywood sense, but they are exactly the kind of physiological surprises that can become mission-level threats because they interfere with function, and they do it inside a closed environment with limited treatment options. So now the picture becomes clearer and more disturbing. Deep space survival is not only surviving obvious hazards outside the spacecraft, it is also surviving the new fluid physics inside your own body. Without gravity, your fluids don't behave the way they do on Earth. That changes pressure relationships. It changes venous return. It changes what happens around the eyes. It changes how the heart and blood vessels adapt. It may reveal hidden vascular risks. And because these changes develop over time, they fit the same pattern we keep seeing throughout this whole topic. Deep space often doesn't break the body with one giant event. It changes the rules slowly until organs and systems start acting like they belong to a different environment, because after long enough, they do. That is the big reveal here. Your eyes, your veins, your blood volume, your pressure regulation. These are not stable background features you can assume will just keep working normally while you fly through space. They are part of the mission. They are being reshaped by the environment, and the longer the mission lasts, the more that reshaping matters. And once you understand that, the next problem becomes even harder to ignore, because fluid shifts and vision changes are still only part of the biological picture. What happens when the immune system starts drifting, microbes stop behaving in familiar ways, and even a small infection becomes something the mission may not be able to handle easily? You don't leave biology behind when you leave Earth. You bring all of it with you, including the parts that can go wrong in ways you don't fully control. That is one of the most important corrections to the way people think about space. A spacecraft looks clean, sealed, technical, almost sterile. It feels like a machine world. But the humans inside it are still biological systems, full of immune responses, microbes, inflammation, healing processes, and weak points. And once a mission lasts long enough, that biology starts becoming one of the main things you have to manage. The first problem is that the immune system does not simply stay normal in space. Studies have shown that immune response can become dysregulated during and after spaceflight. Stress hormones shift. The body is dealing with microgravity, disrupted sleep, confinement, radiation exposure, altered routines, and psychological strain all at once. That matters because the immune system is tightly linked to all of those things. It is not a separate module sitting quietly in the background. It reacts to stress, to sleep loss, to environmental change, and to long periods of strain. And one of the clearest signs that something real is happening is that latent viruses can reactivate in some astronauts. Viruses like Epstein-Barr or varicella zoster can stay in the body quietly for long periods, then reappear when the immune system is under enough pressure. That is a very serious clue. It means even elite astronauts, selected carefully and medically screened at a very high level, are not just staying biologically unchanged in orbit. Their immune systems are being pushed into a different state. That does not mean crews are constantly getting sick in a dramatic way. The point is more subtle and in some ways more concerning. The body is staying functional but under strain. The immune system is adapting and not necessarily in a direction you would choose. In deep space, where missions are longer, radiation exposure is worse, and rescue is not realistic, that kind of immune drift becomes much more important. And then the next problem makes this harder because it is not only the human immune system changing, the microbes inside the habitat are changing too. A sealed spacecraft does not become free of bacteria and fungi just because the hatch closed. It becomes an enclosed ecosystem. The crew brings microbes with them on their skin, in their mouths, in their guts, on their clothes, and on their equipment. Water systems can develop biofilms. Surfaces can collect microbial communities. Air systems have to be monitored. Food systems have to be controlled. The habitat is not sterile. It's an artificial microbiological environment, and like any environment, it can drift. That is one of the reasons deep space habitats are harder to manage than they look. The spacecraft is not just a machine. It's a small living system, whether you want it to be or not. Some microbes also appear to show altered growth patterns or stress responses in microgravity conditions. That does not mean every bacterium suddenly turns into a major threat, but it does mean you cannot assume microbes will behave exactly as they do on Earth. And once you combine that with immune changes in the crew, the overall picture gets less comfortable. A habitat with recycled air, recycled water, limited cleaning options, limited isolation capability, and a crew under physiological stress is not the kind of place where you want microbiology to become unpredictable. So the next question becomes very practical. What happens when a normal health problem stops being normal? On Earth, a small infection is usually not a major event because hospitals, pharmacies, imaging, surgery, and expert care all exist nearby. A scratch, a dental problem, a skin infection, a minor wound. Something that would be boring in everyday life usually stays boring because there are layers of support around it. In deep space, those layers mostly disappear. That changes the whole risk equation. Limited pharmaceuticals mean you cannot carry an unlimited pharmacy. Altered immune function means the body may not respond exactly as it would on Earth. Surgery capability is constrained. Consultation with experts is delayed. Monitoring tools are limited. Recovery space is limited. And every crew member matters, so even one person being partly impaired can affect the whole mission. This is where the phrase routine medical issue starts losing its meaning. A dental abscess is not just a dental problem if it disrupts sleep, causes pain, consumes antibiotics, distracts the crew, and cannot be treated definitively. A small wound is not just a small wound if infection risk rises and healing is slower or more uncertain. A mild illness is not just mild if it spreads in a closed habitat. That is why long-duration survival depends partly on keeping ordinary biology from becoming extraordinary trouble. Deep space does not just punish big failures, it punishes small failures that on Earth would barely matter. And that leads to one of the biggest conceptual shifts in this whole topic. The goal is not sterility. True sterility is not realistic, and in some ways, it's not even the right target. The real target is balance. You need controlled microbial ecosystems. You need safe food production. You need reliable filtration. You need clean surfaces, disciplined hygiene, and continuous surveillance of the habitat's biological environment. That is a completely different frame from the simple idea of keeping the ship clean. It's closer to environmental management. You are trying to keep a small, closed ecosystem from drifting into a state that is bad for human health. That matters because humans are not biologically separate from microbes. We are full of them. We live with them constantly. The immune system itself is shaped by long-term life on Earth inside a rich environment full of invisible biological interactions. When you take humans into deep space, you're not sending isolated bodies into a machine. You're sending complex biological systems carrying their own internal and external ecosystems into a confined environment that has to stay compatible with them for years. That is a much bigger challenge than just preventing germs. It means the mission has to manage the relationship between the crew, the habitat, the water system, the food system, the air system, and the microbial world spreading across all of them. And that is the deeper implication here, one of the most humbling truths in space medicine. You are never just a human inside a spacecraft. You are a walking biome. You are carrying bacteria, viruses, immune memory, inflammation patterns, healing limitations, and biological dependencies that were all shaped by Earth. Then you place that whole system into an environment where radiation is higher, sleep may be worse, stress is chronic, air is recycled, surfaces are enclosed, and water is being used again and again. Under those conditions, staying healthy is not just about avoiding injury. It is about keeping an entire biological balance from drifting too far out of control. That is why the immune system matters so much in deep space. It is not only about disease, it is about resilience. It is about whether the body can stay stable while every major condition around it is pushing in the wrong direction. And once you understand that, the next threat becomes even more fundamental. Because even if infection stays under control, even if the habitat stays clean enough, even if the crew stays medically stable, there is still a slower problem that can weaken everything else. What happens when sleep starts breaking down? The body loses its normal sense of time, and the mission begins to run on a clock the crew has to build artificially just to stay functional. Sleep sounds like a soft issue until you realize that once sleep starts failing, almost every other survival system starts getting worse with it. That is why time itself becomes part of the engineering problem in deep space. Human biology expects a regular day-night pattern. Your circadian system evolved under Earth's roughly 24-hour cycle, with light and darkness acting like built-in instructions for when to be alert, when to slow down, when hormones should rise, when body temperature should shift, and when sleep should happen. On Earth, that timing system is reinforced constantly by the planet. You do not have to build it. You live inside it. In space, that support starts disappearing. In low Earth orbit, astronauts can see sunrise and sunset roughly every 90 minutes as they circle Earth. That is not a normal cue for human biology. On Mars, a day, or sol, is about 24 hours and 39 minutes, close to Earth but not identical. During deep space transit, there is no natural sunrise at all unless the spacecraft creates one artificially. So once humans leave Earth for long periods, time stops being something the environment gives you automatically. It becomes something the habitat has to produce. That is a major shift because it means the mission has to manage not just air, water, food, and pressure, but the body's internal clock too. And if that clock starts drifting, the effects show up everywhere. Poor sleep is not a small problem in that environment. It affects reaction time, mood, immune function, metabolism, and decision making. Those are already important on Earth. In deep space, they become critical because sleep loss also interacts with almost every other stressor the mission is already dealing with. A tired crew is less precise. A tired crew is more emotionally fragile. A tired crew is worse at handling conflict, more likely to make mistakes, less efficient at repairs, less consistent with exercise, and less resilient under pressure. So sleep is not just recovery, it's part of the mission's ability to function. And this is not theoretical. Many space travelers have reported sleep disruption, and sleep medications have been used in orbit. That should get your attention immediately, because even in relatively protected spaceflight, where Earth is still nearby and mission support is much stronger than it would be on a Mars mission, sleep is still a stubborn problem. That means long-duration deep space missions are not entering this area from a position of comfort. They're starting from a point where sleep is already difficult. That matters because deep space is not the kind of environment that gives you extra room to be tired. If your reaction time drops during a landing sequence, if your judgment slips during a system fault, if your mood worsens during a conflict, the cost is much higher than it would be in normal life. Sleep loss does not stay in the bedroom. It leaks into operations. So the next question becomes, if the natural cycle is gone or distorted, how do you protect the crew's internal clock? The answer is that lighting stops being just illumination and starts becoming biological support. Modern habitat design increasingly treats light spectra and timing as medical tools. Blue-enriched light can support alertness at the right times and help reinforce wake cycles. Warmer light can support pre-sleep conditions and reduce stimulation before rest. On Earth, light is mostly just part of the environment. You wake up, the sky is bright, evening comes, the light changes, and your body uses those patterns automatically. In space, those patterns may not exist unless the spacecraft creates them artificially. So light becomes prescription-like. It has to be timed, it has to be tuned, it has to support the crew's internal rhythms instead of confusing them. That means the spacecraft is not only keeping the crew alive chemically and physically, it's also telling their cells what time it's supposed to be. That is a strange but important idea. A deep space habitat is no longer just a shelter. It is a timing machine. If it gives the wrong signals, or inconsistent ones, or signals that the crew cannot follow because the workload is too chaotic, then the circadian system starts drifting. And once that drift grows, sleep quality can get worse. Alertness can become less stable, and the whole mission can start carrying a chronic performance penalty. That gets even worse in isolation, because the problem is not only light, it is the entire structure of time. In analog missions and isolated environments on Earth, researchers have seen how monotony and artificial time cues can distort subjective time perception and routine stability. Over months, people can start feeling detached from normal temporal rhythm. Days blur together, motivation can flatten, routines can become less stable. That may sound abstract, but it has direct effects on morale and consistency. People work better when time feels structured. They do worse when time starts feeling artificial, repetitive, or psychologically thin. Deep space pushes directly into that weakness. It does not just separate the crew from Earth's geography, it separates them from Earth's rhythm. There are no weekends in any meaningful natural sense. There is no weather, there are no seasons in the ordinary human way, there is no outdoor sunrise to reset the mind. There is no ambient social world to reinforce shared timing. The habitat has to create all of that structure, and if it does not do it well enough, the crew can begin to drift not only in sleep schedule, but in how time itself feels. That matters because routine is part of stability. A crew that loses stable rhythm becomes harder to manage at every level. Sleep timing gets worse. Mood gets less predictable. Attention becomes less reliable. Procedures become more vulnerable to inconsistency. And because this happens gradually, it fits the same pattern as many other deep space threats. Nothing dramatic has to happen. The crew just becomes more tired, more flat, more error-prone, and less able to absorb stress. That is the real conclusion here, and it is more serious than it sounds at first. A long-duration mission can fail not only because of a dramatic accident, but because the crew becomes tired in a way that is biochemical, chronic, and cumulative. Sleep loss is dangerous precisely because it weakens so many systems at once. It affects the brain, the immune system, the mood, the metabolism, the quality of teamwork, and the reliability of decisions. When sleep goes bad, almost everything gets harder to manage. And in the deepest sense, that changes what it means to live in space. On Earth, a planet keeps time with you. In deep space, there is no planet doing that work anymore. The crew has to live against the clock they built themselves, inside a machine that has to keep reminding their biology what morning, evening, and night are supposed to mean. That is a bigger problem than it sounds, because once the body loses its timing, all the other stresses of deep space become harder to resist. And if all of that is true, then the next question gets more severe again, because sleep problems are still manageable compared with something even more direct. What happens when a real medical emergency hits, and the farther you are from Earth, the word routine stops meaning anything at all? A medical emergency in deep space is not just a health problem, it can become the center of the entire mission. That is the first thing that changes once you go far enough from Earth. In low Earth orbit, a serious medical situation is still dangerous, but there's at least one idea in the background that helps hold the whole system together. Return is possible. It may be difficult, expensive, and risky, but evacuation is still part of reality. In deep space, that idea disappears. Once you are tens of millions of kilometers away, evacuation stops being an option in any meaningful sense. It becomes fiction. And once that happens, the meaning of a medical emergency changes completely. A severe fracture is no longer just an injury. Internal bleeding is no longer just an urgent case. Appendicitis, a kidney stone, a dental abscess, a dangerous infection, a cardiac event. Any of these can become mission-defining problems. There is no ambulance, there is no emergency room, there is no trauma center waiting on the other end of a fast return. The crew is the hospital, the support staff, the recovery team, and the people trying to keep the spacecraft alive at the same time. That is what makes deep space medicine so serious. It is not only that emergencies are dangerous, it is that they happen in an environment where almost every normal layer of backup has been removed. And then it gets worse because space itself may already be changing the body in ways that raise some medical risks before the emergency even happens. Bone loss can increase calcium excretion, which may contribute to kidney stone risk. That alone is troubling because a kidney stone on Earth is painful enough, but in deep space, it could become a major operational problem. Fluid shifts are already altering normal physiology. Radiation is adding longer-term stress to tissues and cells. Limited movement changes conditioning. Altered immune function can change recovery. Even wound healing and inflammation may not behave exactly as they do on Earth. So the body entering a medical emergency in space may not be in the same state you would expect in a hospital on Earth. And the medicine itself is not automatically reliable in the way people assume. Drug stability can become a concern in space conditions. The way the body handles medications may also shift. That means even the pharmacy is not a simple comfort. The crew may have medications, but those medications exist inside an environment where storage conditions, degradation over time, and altered physiology can all affect how useful they really are. So the medicine cabinet is not just a supply locker. It is part hospital, part chemistry gamble. That is the deeper problem here. Deep space medicine is not only about having tools, it is about whether those tools still work the way you need them to, in a body that has already been changed by the mission. So if Earth is too far away and the body is already under altered conditions, then the next question becomes unavoidable. How capable does the crew need to be medically? The answer is much more capable than today's public image of astronauts usually suggests. Future deep space crews may need advanced autonomous medical capability built directly into the mission. That could mean ultrasound systems, AI-assisted diagnostics, procedural kits for emergency interventions, broader pharmaceutical support, and contingency protocols for serious situations that would normally be handled by specialists on Earth. It also means much deeper cross-training among the crew. On Earth, specialization is efficient. One person is the surgeon, another is the radiologist, another is the emergency physician. In deep space, that model becomes fragile unless every critical skill has redundancy. That changes the whole structure of crew design. You do not just need a doctor, you need people who can operate outside their primary specialty if something goes wrong. You need multiple crew members who understand emergency procedures, imaging, sterile technique, medication use, monitoring, and patient support. You need systems that help non-specialists make better decisions, because there may be no true specialists available in real time. Even if Earth-based doctors can advise, communication delay means the crew still has to carry out the decisions themselves. This is where medicine becomes part autonomy. Just like navigation or engineering, a deep space crew has to be medically independent enough to survive the delay, the uncertainty, and the possibility that the problem is bigger than anything they trained for directly. And that brings us to one of the hardest truths in this section. One serious medical event does not only threaten the patient, it can consume the mission. A badly injured or seriously ill person takes time, attention, equipment, supplies, and emotional energy. Other crew members may have to stop their normal work to monitor the patient, assist with treatment, manage the habitat, communicate with Earth, and adapt mission plans. EVA schedules may need to be canceled. Maintenance may be delayed. Exercise routines may be disrupted. Sleep may get worse for everyone. Stress rises, morale drops. The whole rhythm of the mission can change around one person's condition. That is what makes a medical emergency in deep space so dangerous. It is not just one biological failure inside one body. It is an event that can rewire priorities across the entire closed system. A mission that was built around exploration can suddenly become a care environment. A schedule built around landing or operations can suddenly become a survival schedule. And because the crew is small, every shift in workload matters more. There is no extra hospital team arriving to absorb the burden. The same people treating the patient are the same people who still have to keep the mission functioning. That creates a kind of fragility that is easy to miss from the outside. A spacecraft may look technically stable, but one major illness can pull the crew away from maintenance, planning, and performance at exactly the time they can least afford it. In that sense, the biggest medical danger is not only physical, it's systemic. One biological event can destabilize an entire engineered environment. And that leads to the larger point, which is probably one of the harshest in the whole deep space survival question. Deep space forces humans to confront the fact that health is not only about strength, it's also about distance from support. On Earth, the body can fail and still often be rescued because civilization is built around rescue. Hospitals, pharmacies, imaging, surgery, specialists, ambulances, blood supplies, sterile operating rooms, they're all part of the background structure of modern survival. Deep space strips almost all of that away. So the question becomes much harder than, are humans healthy enough to travel? The deeper question is, how healthy do humans need to be to absorb the fact that when something goes wrong, Earth may be too far away to matter? That is where deep space exploration starts sounding less romantic and more biological. The challenge is no longer only about rockets and courage, it is about whether a human body, already stressed by radiation, microgravity, altered sleep, isolation, and confined living, can survive in a place where routine medical failure is no longer routine at all. And once you understand that, the next problem becomes impossible to ignore. Because even if the crew stays healthy, the habitat itself is aging too. What happens when the spacecraft starts wearing out at the same time the crew's biology is wearing down, and both are trapped together on the same timeline? A long deep space mission is not just about whether the crew can stay alive, it is also about whether the spacecraft can keep acting like a livable world for as long as the crew needs it to. That sounds obvious at first, but most people still picture the spacecraft as the stable part of the story, the hard shell, the reliable machine, the thing protecting the fragile humans inside. For short missions, that picture works well enough. For very long missions, it starts breaking down. Because spacecraft do not stay new. They age, they accumulate damage, and over enough time, the habitat starts entering the same kind of survival race as the crew. That is why deep space survival is really a duel between body degradation and machine degradation. People age in space, obviously, but so does the hardware around them. Thermocycling keeps stressing materials as systems heat and cool. Radiation keeps hitting electronics and structures. The spacecraft carries the memory of launch vibration, earlier maneuvers, and every mechanical load it has already absorbed. Micrometeoroid impacts can leave damage, even when they do not cause immediate crisis. Seals fatigue, materials become more brittle, moving parts wear down, software faults can accumulate, sensors can drift, connectors can loosen. The habitat on day 900 is not the same machine that left Earth. That matters because deep space missions are built on continuity. The crew stays alive only if the ship keeps holding pressure, recycling water, cleaning air, controlling temperature, handling waste, and supporting exercise and medical care for a very long time. So the spacecraft is not just carrying the mission, it is aging through the mission, while the mission still depends on it completely. And that creates a hard question. If the machine is wearing down while the crew is wearing down, which one reaches the dangerous point first? The answer is not simple, because mission designers use redundancy to buy safety. If one system fails, another can take over. That's the logic behind long-duration survival hardware. But redundancy is not the same as invulnerability. Every life support loop needs backups. Every backup needs power. Every power system needs thermal control. Every thermal control loop needs pumps, sensors, and structure. Every additional subsystem adds more hardware, more interfaces, more software, more maintenance, and more places where something can drift out of tolerance. So redundancy helps, but it also creates complexity, and complexity can become its own form of fragility. That is one of the most important engineering truths in deep space design. Redundancy buys time, not immortality. A second pump is useful until the second pump has its own failure mode. A backup processor is useful until radiation or a software issue affects both pathways. An extra valve increases resilience, but also adds another part that can stick, leak, or wear out. This does not mean redundancy is a bad strategy. It means deep space systems have to survive a difficult trade-off. You need enough backup to survive failures, but not so much added complexity that the system becomes harder to maintain than the crew can realistically manage. And that leads to the next reality, because once the mission is underway, maintenance stops being a side task. It becomes part of normal life. Astronauts already spend major amounts of time on maintenance in orbit. Filters need replacing, seals need checking, software needs updating or troubleshooting, environmental systems need monitoring, exercise devices need upkeep, toilets need attention, thermal control hardware can require intervention, experimental equipment breaks, sensors drift, things wear out because that is what machines do. On a deep space mission, that workload does not go away. If anything, it becomes more central. The crew is not just traveling or exploring, they're caretakers of a tiny artificial world that is always trying to drift toward disorder. Every day, the habitat is aging a little more, and the crew has to keep pulling it back toward stability. That changes the role of the astronauts in a major way. They're not just pilots, scientists, or explorers. They're also maintenance personnel for a complete life support ecosystem. They have to inspect, repair, clean, monitor, recalibrate, and work around failures while still doing everything else the mission requires. That consumes time and energy, and it creates another place where fatigue and crew degradation can feed back into system risk. If the crew gets more tired or less sharp, maintenance gets worse. If maintenance gets worse, the habitat degrades faster. That's the kind of loop that makes long missions hard. And then the next problem becomes unavoidable, because no matter how good the maintenance plan is, there are limits to what you can carry. You cannot launch a full hardware store into deep space. Spare parts are limited by mass and volume. That means mission designers have to be selective. They have to guess which parts are most likely to fail, which failures are most dangerous, and which items are worth the launch cost. That pushes them towards modular systems, repairable architecture, fault-tolerant software, and in some cases, in-situ fabrication like 3D printing. Those approaches help, but they're not magic. A modular design can make repairs easier, but only if the crew has the right replacement module. A 3D printer can produce some parts, but not every part. It may help with brackets, housings, simple tools, and selected components, but not necessarily with high-stress parts, precision seals, advanced electronics, or components that require special materials and certification. So in practice, repairability improves resilience, but it does not eliminate scarcity. That is where the deeper unease comes in. The farther humans go, the more they depend on machines that everyone knows will slowly age, in a place where full replacement is impossible. The spacecraft is not a temporary shell waiting for support from Earth. It is the support. And if it starts losing capability faster than the crew can restore it, the mission begins to narrow. Not at all once, but gradually. A system becomes less efficient. A backup becomes unavailable. A repair becomes temporary. Margin gets thinner, then thinner again. That is why long-duration mission design breaks a very common intuition. Most people assume the crew is the vulnerable part, and the spacecraft is the stable shell around them. But the longer the mission lasts, the less clean that distinction becomes. Crew and craft may degrade together. The human body loses muscle, bone, cardiovascular conditioning, sleep stability, and biological margin. The spacecraft loses material margin, hardware margin, software margin, and spare part margin. And these two forms of degradation are tightly coupled. The crew depends on the craft to maintain air, water, pressure, temperature, hygiene, and structure. The craft depends on the crew to inspect it, repair it, clean it, and keep it running. If one side gets weaker, the other side gets more vulnerable too. That is the real break in intuition. The habitat is not just a tool. It becomes something much closer to a second body. It circulates air the way a body circulates blood. It processes waste, it regulates temperature, it defends against a hostile outside environment. It has sensors, control systems, and structural boundaries that have to stay intact for the humans inside to remain alive. And just like a biological body, it can stay functional while slowly accumulating wear, until one day the hidden cost of that wear becomes impossible to ignore. That is one of the clearest reasons deep space survival is so hard to answer with one number. It is not just about how long humans can endure. It is about how long the entire combined system, human biology plus habitat engineering, can stay above the failure threshold together. And once you see that, the next section becomes the one the whole video has really been building toward. So after all of this, after air, water, food, radiation, psychology, immunity, sleep, medicine, and hardware wear, how long could humans actually survive in deep space? Not in theory, but in realistic time horizons. So after all of that, what is the real answer? How long could humans actually survive in deep space? The most honest answer is that the timeline is not one clean number. It comes in layers. Some time ranges are already within human capability. Some look plausible but risky, and some start pushing past exploration into something much harder. So if you want the straight answer, it goes like this. Days to weeks in deep space are absolutely possible. That part is already inside demonstrated human capability. If you have reliable pressurization, working life support, stored food and water, and a plan for radiation shelter during solar events, humans can survive in deep space for short missions. Apollo already proved that people can leave low Earth orbit, travel through cislunar space, reach the moon, and come back. Those missions were dangerous, but they were real, and they showed that humans can function beyond Earth orbit for meaningful periods. That matters because it sets the baseline correctly. Deep space is not automatically beyond us. Humans are not instantly destroyed the moment they leave Earth's magnetic protection. With the right systems, days or weeks are clearly achievable. A short mission is still full of risk, but the risk is within a range that has already been faced and managed before. Then the next question is, what about months? That is where the answer becomes more careful but still fairly strong. 6 months to a year in space has already been demonstrated multiple times in orbit. Human beings can stay alive in microgravity for long durations. They can work, adapt, and function. So when people ask whether months-long deep space missions are possible, the answer is broadly yes. With current or near-current systems, especially in cislunar operations, missions lasting months are plausible. But there is an important limit on how confident that answer should sound. Orbit data do not transfer perfectly to deep space. The reason is simple. In orbit, you still have partial protection from Earth's magnetic field. You still have faster communication. You still have at least some emergency return option. Deep space removes or weakens all of those. So when we say months are plausible, we are partly leaning on orbit data and partly extending it into a harsher environment. That means the answer is strong, but not complete. We know humans can do months in space. We have good reason to think they can do months in deep space too. But the biological and operational cost would be higher than what orbit alone suggests. And that takes us to the timeline that matters most for real exploration planning, about 2 to 3 years. This is where the debate becomes serious. A Mars-class mission using a conjunction-class architecture can stretch to roughly 900 days, depending on how the mission is designed. That includes outbound transit, surface stay, and return. And this is the time range where most of the problems we've been talking about stop being manageable side issues and start stacking into a real long-duration survival challenge. Could humans survive that long in deep space? Very possibly, yes. Could they stay alive through it with a well-designed mission? Probably yes. But once you ask a more demanding question, the answer gets less comfortable. Would they still be healthy in a strong sense at the end? Would they be physically capable, cognitively sharp, psychologically stable, medically resilient, and operationally effective after that full duration? That is much less certain. This is why the Mars-class regime is the real boundary zone. Radiation exposure by then is no longer a minor cost. Deconditioning is no longer temporary discomfort. Psychological strain is no longer something you can dismiss as part of the adventure. Hardware wear is no longer a background concern. Everything has had time to accumulate. That doesn't mean a Mars mission is impossible. It means survival and mission success are no longer the same thing. A crew might arrive alive, return alive, and still pay a very serious biological and operational price. That's the key distinction. For a Mars-class mission, the question is probably not, can humans remain alive? The harder question is, can they remain high-functioning long enough to complete every phase safely? Then the next question is the one that starts changing the whole frame. What about beyond that? 5 years, 10 years, 20 years? At that point, biology starts demanding a different answer. Not necessarily no, but not with the same kind of spacecraft people usually picture. If you're talking about humans surviving in deep space for many years, you probably have to stop imagining a simple capsule or transit vehicle. You have to start imagining something closer to a semi-closed ecosystem. That means serious radiation mitigation, not just minimal shielding. It probably means some kind of partial or artificial gravity strategy, because microgravity damage becomes harder and harder to tolerate over very long spans. It likely means robust food production, not just stored meals. It means advanced autonomous medicine, because you can't keep stretching duration while relying on Earth-based rescue assumptions. And it means extremely reliable maintenance systems, because the habitat itself has to survive years of wear without constant replacement from Earth. In other words, once you go beyond several years, you're not just extending a mission. You're trying to transplant enough of civilization's support systems into space that human biology can keep working there. That is a different category of project. And that is why the answer becomes so much harder. Could humans survive 5 or 10 years in deep space? Possibly, but only if the habitat starts behaving less like a spacecraft and more like a portable environment, almost a small world with its own stable internal systems. Without that, duration stops looking like endurance and starts looking like attrition. So what is the honest answer after all of this? With foreseeable technology, humans can likely survive in deep space for months to a few years. That is the range that seems most realistic without needing a completely different level of civilization in space. Short missions are already within demonstrated reality. Months-long missions are broadly plausible. Mars-class durations may be survivable, but with major accumulated risks that are still not fully solved. Going much beyond that without major advances in radiation protection, artificial gravity, closed-loop ecological support, and autonomous medicine starts looking less like exploration and more like gambling against multiple slow failure systems at once. That is the real answer. It is not that human beings are too weak for deep space. It is that deep space is very good at exposing every system humans normally get from Earth for free. And the longer the mission lasts, the more completely those missing systems have to be rebuilt artificially. And once you see that, one final question becomes unavoidable. If months are possible and a few years may be possible with major risk, then what technologies could actually push that survival limit outward, and which of them would change the game the most? If humans are going to survive longer in deep space, it probably will not come from one miracle invention. It will come from a set of technologies that reduce the damage from multiple directions at once. That is the key point going into this section. There is no single machine that suddenly makes deep space safe. The problems are too broad for that. Radiation, microgravity, food stability, medical isolation, hardware wear, and crew performance all push in different ways. So the technologies that matter most are the ones that either remove a major source of damage or give the crew much more margin against it. And the first one is probably the biggest. Artificial gravity could change almost everything. A lot of the problems in long-duration spaceflight trace back to the fact that the human body is living in zero-G for too long. Muscle loss, bone loss, cardiovascular deconditioning, fluid shifts, maybe even some of the eye-related issues. All of these are at least partly tied to the absence of gravity. So if a spacecraft could provide meaningful gravity, even partial gravity, it could reduce several mission-threatening problems at the same time. The basic physics is not mysterious. If you rotate a habitat, centripetal acceleration can imitate gravity for the crew inside. In simple terms, rotation can press the crew outward in a way that feels gravity-like. That idea has been around for a long time, and it's still one of the strongest long-term solutions anyone has for keeping human biology closer to normal in space. But the engineering is much harder than the concept. You have to think about rotation rate, because if it spins too fast, people may get motion sickness or other sensory problems. You have to think about radius, because a small rotating habitat may need to spin faster to create the same gravity level. You have to think about structural mass, because once a spacecraft starts rotating, the loads and design requirements change. You also have to think about docking, because connecting with a rotating system is not simple. You also have to think about whether you want full Earth gravity, partial gravity, or some intermittent artificial gravity strategy. So artificial gravity is probably one of the most transformative options on the table, but also one of the hardest to implement well. Still, If it works, it changes the mission at a very deep level. It does not just treat one symptom, it changes the environment, causing multiple symptoms. Then there's the next technology lever, and it's much more direct: faster propulsion. A lot of deep space danger is a time problem. The longer the trip, the more radiation the crew takes, the more muscle and bone loss they accumulate, the more food and water they need, the more sleep and psychological strain build up, and the more time the spacecraft has to wear down. That means one of the cleanest ways to improve survival is simply to shorten the transit. That is why nuclear thermal propulsion and other advanced propulsion concepts matter so much. If they can reduce trip duration to Mars compared with conventional chemical systems, they don't just improve convenience, they reduce exposure across almost every major category. Less travel time means less radiation dose. It means less deconditioning. It means less life support demand. It means less time for hardware to fail. It means fewer chances for medical and psychological problems to accumulate. This is one of the rare areas where one engineering improvement helps almost everything else indirectly. It does not remove the need for shielding, exercise, medicine, or good life support, but it compresses the timeline those systems have to cover, and that alone is a major survival gain. Then we get to radiation, because even with better propulsion, shielding still matters. The ideal deep space spacecraft wouldn't rely on a single giant protective wall. It would probably use smarter shielding in layers. Hydrogen-rich materials are important because they can help against some charged particles without the same drawbacks as very dense, high atomic number materials. Water can be useful here too, especially if it's placed strategically. Vehicle geometry matters because you can arrange supplies and tanks to protect crew spaces better. Dedicated storm shelters for solar particle events because a crew may need a more heavily shielded area for short periods of intense exposure. There is also ongoing interest in more advanced ideas like magnetic or plasma shielding. None of those is a complete operational answer yet, but the important point is that deep space survival may not depend on one perfect shield. It may improve through many smaller reductions layered together. Better material choices, better layout, better shelter design, better transit time, all of those together can change the risk curve. That matters because radiation is cumulative. Even modest reductions help if they're applied consistently across the mission. So smarter shielding is less about a dramatic breakthrough and more about reducing exposure enough that a mission becomes more biologically tolerable on the mission. Then there's a technology lever that changes the mission even more fundamentally: bioregenerative life support. Right now, long missions still lean heavily on stored supplies and mechanical recycling. That works up to a point. But the moment a habitat can recycle more completely and produce a meaningful fraction of its own food, oxygen, and water support biologically, the entire mission changes. Duration stops being tied so tightly to launch mass. The spacecraft starts moving away from expedition logic, where you bring what you need, and towards settlement logic, where the habitat supports more of itself over time. That is a giant threshold. If plants, microbial systems, and tightly managed ecological loops can take over more of the work, then the mission becomes less dependent on stored cargo and more dependent on internal regeneration. That could improve nutrition, reduce mass pressure, support oxygen and humidity control, and make much longer missions more realistic. But of course, it also adds complexity, because living systems have to be maintained, balanced, and protected from drift. So biogenerative life support is not a shortcut. It is a more powerful, but also more biologically demanding version of life support. And then there is the final category, which may end up being essential even if every other system improves: medicine, AI, and autonomy. The farther humans go from Earth, the less they can depend on Earth to think for them in real time. That means the spacecraft itself has to become smarter and more supportive. Autonomous diagnostics could help crews identify problems faster. Robotic assistance could help with repairs or medical procedures. Wearable health monitoring could catch early signs of trouble before they become full emergencies. Predictive maintenance systems could warn crews that hardware is drifting toward failure. Onboard decision support could help with troubleshooting, treatment, scheduling, and risk management when communication delays make outside help too slow. This is one of the biggest shifts in deep space design. The spacecraft cannot just be a vehicle with supplies. It has to behave more like an active support system. The farther out you go, the more it has to act like a doctor, a mechanic, an environmental engineer, and in some ways, even a psychologist. It has to help the crew stay healthy, stay organized, and stay ahead of failure. That sounds futuristic, but deep space may make it non-optional. Because once you remove quick rescue, fast consultation, and easy resupply, the habitat has to absorb those missing functions itself. So when you step back, the picture becomes clearer. The technologies that could push the survival limit outward are not random upgrades. They attack the core failure mechanisms directly. Artificial gravity fights deconditioning. Better propulsion cuts exposure time. Better shielding reduces radiation burden. Biogenerative life support reduces dependence on stored mass. AI and autonomy reduce the penalty of distance. None of these fully solve deep space on their own, but together they start moving human missions away from the model of a fragile crew trying to endure a hostile trip and toward the model of a stable human environment that can keep people functional for much longer. And that brings us to the final answer of the whole video. Because once you know the limits, and once you know what could push those limits outward, the last question becomes the most important one. So what is the final truth here? Could humans survive in deep space for a long time? And if they can, what would they have to become in the process? Could humans survive in deep space? Yes, for months, certainly. For a few years, probably with major risk. For much longer than that, only if we build systems that replace more and more of what Earth has always been doing for us in the background. And that is the real trap in this whole question. It sounds like survival is mainly about human toughness. It is not. It's about how completely you can substitute for Earth. That is the shortest, honest answer. Humans are not too fragile to leave Earth. We already know that. We have done it. We know the body can survive in space for meaningful lengths of time. We know crews can work, adapt, and endure. But deep space changes the rules because the farther you go, the less Earth is helping you. So survival stops being a question of simple endurance and becomes a question of environmental replacement. Can your spacecraft replace pressure, air quality, water cycling, food stability, gravity loading, radiation protection, medical support, sleep timing, and biological balance well enough for long enough? That is the real test. And once you say that way, one of the biggest myths about space falls apart immediately. The myth is that space is empty, so the challenge is mostly distance. Build a strong enough rocket, go far enough, and the rest is just travel time. But the truth is much harsher and much more interesting. Space is not just far away. It's biologically hostile in many subtle ways at the same time. It pushes on muscle and bone because gravity is gone. It pushes on cells because radiation is higher. It pushes on the eyes, the blood, and fluid balance because the body is no longer living under normal weight. It pushes on mood, judgment, and teamwork because isolation becomes part of the environment. It pushes on immunity, on microbes, on logistics, on medicine, on hardware reliability, all at once. That's what makes deep space so difficult. It doesn't usually come at the body with one dramatic attack. It chips away across multiple systems together. A little more radiation, a little less muscle, a little worse sleep, a little more stress, a little more hardware wear, a little more uncertainty. And over time, that combination becomes the real threat. The danger is cumulative. The danger is system level. The danger is that the body and the habitat can both stay functional for a long time while still drifting toward the edge. And that leads to the deeper perspective this whole topic points toward. Life on Earth is not just life on a planet, it's life inside a complete support system. We usually don't think of it that way because we're inside it all the time, but Earth is constantly doing work for us. The atmosphere gives us pressure and breathable air. The magnetosphere reduces radiation exposure. Gravity keeps muscles, bones, blood flow, and body orientation in a familiar state. The water cycle supports life continuously. The light-dark cycle keeps circadian rhythm anchored. The biosphere around us, including countless invisible organisms and ecological interactions, stabilizes life in ways most people never have to think about. Deep space strips that away. And that means every extra month a human survives out there is not proof that the human body was always meant for space. It's proof that we managed to carry enough Earth with us to keep the body functioning anyway. That is a very important difference. It changes the emotional meaning of exploration. Surviving in deep space is not mainly about escaping Earth. It's about rebuilding enough of Earth in a place where Earth no longer exists. And that's why the future of real deep space survival probably doesn't look like the old fantasy of just sending tougher astronauts farther away. If humanity wants to become a true deep space species, the answer may be much bigger than personal toughness. It may mean rotating habitats that provide gravity-like loading. It may mean closed ecosystems that recycle and regenerate more like living environments than machines. It may mean much stronger radiation protection, new propulsion systems that cut travel time, autonomous medicine that functions without Earth, and maybe even deeper biological interventions over time. The habitats may need to become less like vehicles and more like portable worlds. That's the scale of the challenge. Not just bigger rockets, bigger biology, better environments, more complete replacement of the systems Earth has always given us for free. And that's the unsettling part, because it means the real path to surviving longer in deep space may not be learning to live with less Earth. It may be learning to carry more of Earth with us. So after everything in this video, after the air problem, the water problem, the food problem, the gravity problem, the immune problem, the sleep problem, the medical problem, and the machine wear problem, the final answer is this. Humans could survive in deep space long enough to leave Earth behind, but not long enough to stop needing it. And that may be the most important thing space has taught us so far. Before humanity can truly master deep space, we have to understand how completely our bodies were shaped by Earth, and how much of that world has to travel with us if we want to stay human while we go farther than ever before. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.